So far, we have been concentrating only on the issue of making a process statistically stable and controlled, which is very important. But once we have mastered this, it is time to assess the performance of the process vis-a-vis the voice of the customer. We never brought the voice of customer into the equation at all, because we wanted to make sure the process is in control, stable, reliable. So now that we have achieved it, let's bring the voice of the customer into the equation. If you may recall, the voice of the customer is expressed through the target value, the USL and the LSL. So what we need to do is to superimpose these three values on the process, which has its own LCL and UCL and the center, and see the implications of that. But before doing this, it's also important for us to develop some basic insights about how good a process is inherently going to be. So we look at that and then superimpose these values on the top of it. You have a plot here. There is a process A which is indicated by the blue line. There is a process B which is indicated by the red line. Both are normal distributions. Both the processes are identically centered at this point. The only difference though is process A, which is the blue line, has a very wide spread indicated by a very long gap between upper control limit and lower control limit, right? And process B is having a lower spread, because this is where is the spread of the process, although they are both are centered identically. Of course, we have superimposed the customer parameters. These are the specifications, LSL and USL. Now, before getting into the customer parameters, the question is, which process is better? Is it process A or process B? The shaded area is defect because it is beyond the specification limits. So process A has the potential to generate defects because its spread is beyond the USL or the LSL, whereas process B is not. So in general, what we can say is process B is better than A, and to generalize this argument, all other things being equal, spread of a process is indicative of its capability. Lesser the spread, better is the process. So this has a lower, process B has a lower spread, so process B is better. Now let us look at another situation where there are two processes A and B which have identical spread, because as you see here, the gap between the LCL and UCL of the red line is the same as the gap between the LCL and UCL of the grey line. So process A and process B are identical. Now the question is, which one is better? Very clearly, process A is better. Why? Because process A is centered on the target. The center of process A is the same as the target, whereas in the case of process B, there is an offset indicated here. This is the center of process B and this is the customer's requirement in terms of target. So there is an offset. So clearly process A is better than process B. In other words, what we are saying is, if you have to choose between two processes which are identical in terms of their capability, then a process that is aligned closer to the desired target is likely to be more capable, simply because all these region are defects. It is beyond the specification limit. So all these are going to be defect. So process B has more propensity to generate defects out of the process compared to process A. So if you summarize all these learnings from these two graphs, first of all, process capability is defined by the spread of the process. Potential capability, what is the potential of a process? So this measure is called CP, potential capability is called CP. CP is the ratio of specification range to the process capability indicated by USL minus LSL over 6 sigma. The 6 sigma are the plus or minus 3 sigmas that we are talking about. There is a third which is called actual capability. It is indicated as CPK, and that takes into consideration the extent to which the process has deviated or offset from the target. Now, why do you want to calculate CPK? The calculation looks very simple, but the question is, why do we want it? Now, let us look at a table which will tell us what is the value of knowing CPK of a process. So, here is a table which relates the CPK to how much defects the process will produce. A process with a CPK of 0.25, the defects will be 453,255 parts per million. It goes on. For a process with a CPK of 1, the defects dramatically fall down to 2,700 parts per million. Let us say a CPK of 2, essentially the defects are 0.0018 parts per million. In other words, it is 1.8 parts per billion. That is what this number is. Now, CPK 2 is exactly a 6 sigma organization. So, CPK is a very good measure to predict defects coming out of a process. It could be used to target improvements in the process. For instance, we can monitor the CPK, and if it is at 0.5, we can set a target. By the end of the year, I want the CPK to be 0.75 or maybe 1. That is one use. Or suppliers could be asked to submit their CPK levels, and it can be continuously monitored. So, that is another use of CPK. And finally, a 6 sigma organization is one which is able to achieve a CPK value of 2. So, that is what a 6 sigma is all about. Continuous improvements, statistically stable controlled process, very narrow spread, all of them can take organizations to a value of CPK of 2. I hope you will find gainful application of these tools to your work setting. In the next video, we shall discuss some issues pertaining to service quality. While we did take some service examples to set up control charts and so on, there are still some interesting challenges, specific issues when we talk about quality in a service that we will see in the next video.